So in today's lecture, we start lecture 29 in the helicopter dynamics series. And today I'm going to discuss the FEM approach, the assembly of the element mass stiffness matrix and the virtual work related force vector which we derived in our previous lecture. And this is going to lead us to the global mass and stiffness matrices. I'm Dr. Ranjan Ganguly. Now, in the previous lecture, we have derived T, V, and delta W in a local sense, and thus we have obtained the energy values within each of these elements. Now, the problem is that when we want to apply the physical laws, we need to find the total energy of the system. And we are going to apply the Lagrange equation, but for that we need to calculate T total, V total, and delta W total. Now recall that T was the kinetic energy of the system, V is the strain energy of the system, W is the virtual work for the system, and the subscript TOT here represents that these are for the total system, for the entire beam in this case. So let's start with a very simple model of the beam. So we divide the beam into three segments, and each of these segments or parts has 4 degrees of freedom. So there are 2 degrees of freedom here, 2 degrees of freedom here, 2 here, and 2 here. So the interesting thing to see here is that though there are a total of 8 degrees of freedom, there are some common degrees of freedom. So between this segment and this segment here, there are these common degrees of freedom 3 and 4. Between these two segments, the common degrees of freedom 5 and 6. So we have to figure out some way to get these things together. Now how we do that is we are going to get the strain components coming out of each of these three segments. So let us look at the first one here. Now we take the 8 degrees of freedom and we realize for the first segment only the first 4 degrees of freedom are there. So the numbers from the matrix for this segment are only going to populate the part of this complete matrix which corresponds to 1, 2, 3, and 4. Okay, so this 4 by 4 matrix is going to come here, and for simplicity we are going to call this complete matrix as K 1, 2, 3, 4 because it corresponds to degrees of freedom 1, 2, 3, 4. Now we go to the next segment here. Now we saw that the next segment corresponds to 3, 4, 5, and 6. So the matrix comes here. I'm just using zeros as markers here. These are not actually zeros. I'm just saying that the terms of the K matrix come here corresponding to the degrees of freedom 3, 4, 5, and 6. And for simplicity, I call this K 3, 4, 5, 6. Now we come to the third segment, and this corresponds to Q5, Q6, Q7, Q8. Okay, the last 4 degrees of freedom in the beam. And so my stiffness matrix goes here, the 4 by 4 stiffness matrix comes here, and for simplicity I write this as K 5, 6, 7, 8. Now what I do, I want to put all these matrices together. So I essentially create K total as the sum of these three matrices, and you can clearly see that that's the first matrix, that's the second matrix, and that's the third matrix, and these terms here are summed. So here this is contribution X plus contribution from this 0. So these are summed together, these are summed together. So a simple way to do it would be to create each of these three matrices and then sum them. But of course, there are more smart ways of doing it when you are doing computer programming. You can build this entire matrix together and just put it at the appropriate places. Okay. So you can see now that the total stiffness matrix which we have obtained has 8 degrees of freedom corresponding to the complete beam, and as you would expect, this is the first part, this is the second segment, this is the third segment. Okay, whichever parts you see, there is a mixing of the components from the element 1 and 2. Those correspond to the degrees of freedom which are common to elements 1 and 2. So those were Q3 and Q4. And similarly here, the degrees of freedom common are Q5 and Q6 between the element 2 and 3. And so here there is a summation of these parts also. So now this kind of matrix which you often get in finite element analysis is sometimes known as a banded stiffness matrix, because lot of these elements are essentially zero. So all these elements are zero here. That sometimes makes it simpler for doing some numerical calculations and also for storage. You don't need to store the entire matrices in some cases, but again that is typically done in more complicated programming of large systems. If you are dealing with a simple rotating beam type problem, you may not need to practice some of those theories. Now exactly similar mindset can be used to obtain the mass matrices, which are also 4 by 4. So you would similarly put together the mass matrices and combine them and sum them at the total level. While summing, just remember to place the elements exactly where they should be in terms of the degrees of freedom. Now we can clearly see that this assembly process is very easy and can be programmed in a computer. And one of the reasons for the success of the method here was that a lot of the mathematics is easily programmable on a computer, and that is why the Galerkin and Rayleigh-Ritz method quickly gave way to this method once the computers came up. So process which we did before, essentially we can now write it in this form. We can think about the entire term here for energy, and so that would be half the degrees of freedom dot m dot into q here, and similarly you would get q here. Okay, the force vector terms, again you would combine 1 2 3 4 with 3 4 5 6 with 5 6 7 8, and summing the degrees of freedom corresponding to 3 4 3 4 and 5 6 5 6. So now that we have done this, we essentially have expressed the different energies in terms of the degrees of freedom corresponding to the complete system. And now we can invoke the Lagrange equation in a manner which was done for the Rayleigh-Ritz method, because we have access to the complete values for the entire system. So we have T dot and we have V dot and we also have Qi, and we have all these expressed in terms of the degrees of freedom for the system. So once you do that, you obtain the complete global equation of motion for the system for the beam in this particular problem. And as you would expect, we have taken 8 degrees of freedom. Therefore, you have a 8 by 8 mass matrix. You have a 8 by 8 stiffness matrix. You have the 8 degrees of freedom here, and you have a 8 degree of freedom force vector. So now this is an equation with which most people are very familiar whenever they are working in structural dynamics. This is nothing but a multidimensional form of the spring mass force equation. So this is m q double dot plus k, q is F. Now there are certain intricacies here which need to be addressed. One is that you are going to find, if you try to find natural frequencies, that this matrix is going to be singular because rigid body modes are involved. And that is because we have not imposed any boundary conditions on this problem. Now essentially this current equation is valid for a free beam. Okay, and a free beam essentially has free boundary conditions at both ends, that is the moment is 0 and the shear force is 0. So there are going to be some zero frequency modes present here. You can imagine if there is a free beam, there is going to be a pure vertical motion and there is going to be a seesaw type motion present in this beam, which are the two modes, which are zero frequency modes. So we need to remove this or we are going to encounter these singularities. Now for a typical helicopter blade, we would like to impose boundary conditions on this problem to bring in the physics of the problem. So let's start with the cantilever boundary condition or the cantilever beam. Now the cantilever beam has the geometric boundary condition that Q1 and Q2 are 0. So now that boundary condition that W is equal to 0 and the first derivative of W equal to 0 manifests itself in this form in terms of the degrees of freedom. Always remember Q1 was the displacement and Q2 was the slope. So these boundary conditions exist at R is 0. And from our discretization of this into three segments, we know that this is only impacting Q1 and Q2 for segment 1. So essentially the cantilever condition means that the beam is fixed at one end and free at the second end. That's the cantilever beam boundary condition. Some people don't like to use the word cantilever boundary condition because actually there is only either a fixed or a free boundary condition. But we could say that this is the boundary condition for the cantilever beam. Now we actually don't need to know Q1 and Q2 as they are 0. Therefore, what we do is we can drop the first rows and columns in the global matrices corresponding to Q1 and Q2. So here you see that I have written down the truncated mass and stiffness matrix and force vector. All these are global quantities. And I have simply dropped the first row and column corresponding to Q1 and Q2. And this has given me these nice matrices starting from 3, 3 here and Q3 here. And the degrees of freedom Q1 and Q2 has been dropped. Now if you work with this matrix and you try to find the natural frequencies corresponding to this mass and this stiffness, you are going to get a solution which is going to be the rotating frequency of the cantilever beam. And if your mass and stiffness correspond to the rotating beam, that is they include the effect of centrifugal force, then this is going to be essentially the rotating beam frequency, and you can also get the mode shape. So very nice and interesting way to impose boundary conditions here. We did it in a very clever manner. And of course, one thing you will note is that the element we have constructed here does not necessarily satisfy the force boundary conditions because we have only access to Q1 and Q2. So essentially the displacement and slope in terms of the degrees of freedom, we don't have access here to the moment and shear force. So we are going to apply the geometric boundary conditions and discretize this mesh sufficiently well and hope for the best in terms of satisfaction of the force boundary condition. So in the next lecture, I am going to discuss simply supported boundary condition that is corresponding to the articulated helicopter rotor. So remember, the cantilever boundary condition is for a hingeless type of rotor and the simply supported boundary condition is for the articulated type of rotor. See you then.